let's do some fun stuff. We're working on the moment of inertia and the moment of inertia tensor and the angular momentum. So, and I want to calculate the moment of inertia tensor for 3-point masses, and then use and pick an angular velocity and then calculate the angular momentum from that. So we're going to do some stuff. We're going to do this all in Python. We're only going to use 3 masses just so it's easier to see. But here's the point. If you can do this for 3 masses, you can do this for 8 million masses. There's no difference, right? Especially if we're using Python. And that's what I want to do. So I have these 3 masses right here. I just picked some values. I picked the locations. It's not a big deal. We can change it up because they're just points. And we have our angular momentum equation where we have the moment of inertia tensor times the operated on the angular velocity vector, where we define the moment of inertia tensor as this tensor ixx, ixy, ixz, and these elements we can calculate. Ixx, we take each mass and we multiply its mass by its y value squared plus its z value squared, and then add all those up, and that's ixx. And then for something like ixy, we take negative each mass times its x value times its y value and add all those up. And then we can do the same thing for iyx, which would be the same as this, right? Because if I flip the order of these two, I get the same thing. We can do this for yy. It's just going to be x squared, z squared. We can do zz. It's going to be x squared, y squared. We can do yz. It's going to be yz, and so forth. So we can do all this stuff. We're going to do some stuff with functions and with lists using, and this is important here, web, well, I can't even spell it, web v Python. Because web v Python does not have matrix operations in it. We do not have that in there. So we're going to have to come up with another way to do it. And I want to still do web v Python because I like it, and you don't have to install anything. There's a bunch of reasons. So I've already made a program with these 3 masses, and the first thing I want to do is to calculate the center of mass. So we can define the center of mass, rcom, as the sum over I, mi, ri, magnitude squared. No, that's not right. I'm thinking of I. It's going to be the sum over I, mi, ri over the sum over I. That's it. Okay, so we're going to do that first. So let's do that. I already started a program. I didn't want to waste time making a bunch of masses, so let's just see what we have here. This is the program I have. I have 3 masses. They're just at different locations. It doesn't really matter. I have momentums and stuff because I actually was making this rotate too, but that's another day. So if I run this, let's just see what it looks like. There's my 3 masses. And it is in 3D. You can rotate it around if that makes you happy. It makes me a little bit happy. So I want to calculate the center mass. And I'm going to make this as, let's just do this, and then let's turn it into a function. So the first thing I'm going to do is to make a list of my masses. Not just the mass values, but everything. So let's work on lists. So let's call this masses equals a list. And I'm just going to say mass A, mass B, mass C. And we could add this in other ways, but that's my list. And let me show you how this works. This is the 0th element, the 1 and the 2 element. So they all have numbers. Now I could print out the position of mass C. Let's do that. Print mass C POS equals. So that would be masses 2, right? That's the 3rd element in there. I can't print masses 2 because it's a 3D object. It's a sphere. I can't print a sphere, but I can print the position. So .pos. It's the same as printing mass C.pos. Run that, and there it is. It's kind of cool, right? Okay. So I have a list of things, and I have the masses too, right? Mass 2.m mass. I can print that out too, because I associated the mass with the property, as a property of that object, and that's going to make things really easy. So let's calculate the center mass. I'm going to call this rsum, which isn't really the thing. But what I want to do is to go through and take mass times position and add them all up. In order to do that, I need to start, I'm going to add them to this thing, but I need to start with something. So I'm going to call this 0. Oh, it's going to be a vector. Vector 0, 0, 0. And I'm going to have msum equals 0. That's a scale. That's going to be adding up all the masses. And again, you could do this manually. It's not hard. But we're doing this with 3 masses because then when we do it with 8 billion masses, it's the same idea. I'm not going to do 8 billion. That's crazy. So let's do this. Here's a cool trick. For in masses. So this is, no, not form, for. Let's just do this. For in masses, print POS equals dot.pos. So this will go through that list and call each element in there and then I can do with it what I will. You could do something like have an index I and go through with masses zi and print it, but this is a really cool way to do it. It's really short too. So if I run that, you see I get the positions of all the masses, and that's kind of cool. I think that's cool. Okay, so we're going to use that to calculate the center mass. So I don't want to print. What I want to do is to add rsum equals rsum plus mm.pos times mm.m. mm.pos is the position, mm.m is the mass. So I'm adding all those up, and it's not rsum. It's really that top part. And now I need to do that for the bottom too. msum equals msum plus mm.m. And so now I'm gonna have everything I need to calculate the center mass. So rcom is going to be rsum divided by msum, and let's print that out. Print rcom, that's center mass, is rcom, and then the units are meters. And this will be really useful when you calculate the so there's my center mass, and I think that makes sense. It seems like it's in the right place. I'm pretty happy with that. But I want to do one more thing. Let's actually make this a function so that I can call it, and that'll be useful again in a later situation. So I'm going to say def rcom, and I'm going to give it a list. I'm going to call it ms. So, and I'm going to put all the stuff in there. So I'm going to tab that in. I'm not going to print that right there. Well, actually, I could have done that. Let's do that. Okay, so this is a function, and I'm going to pass it some list of things, and we should put that in here. ms is a list of masses, because if I pass it the wrong thing, it's not going to work. And so you should add comments. I'm not going to put a lot of comments just for speed. So that's what I'm going to pass to my list. So this rsum, still I need that. msum is the same. But now I'm going to change this mm in ms, right? Because ms is the list of my masses. But the rest of that's fine. And then I calculate the center mass, which I can't call it that. Rcom temp, because the name of my thing was rcom. Actually, I could just return that. So then we want to return this. And so when I print rcom, I'm going to call the function with masses. It's going to be the center mass of the list of things called masses. And this is going to be great. So I get the same thing, but now it's a function. And the great thing is, this could be a list of as many things as I want, and it's still going to work. Okay, now let's make a function to calculate the moment of inertia tensor. So we have a problem here in that there is no tensor, right? So I don't have a tensor. Instead, what I'm going to do is to define a list of vectors. So let me show you how I'm going to write this. So let's switch over to the paper. So let's write this out. I equals IXX, IXY, IXZ, IYX, IYY, IYZ, IZX, IZY, IZZ. So I don't have a matrix, but what I'm going to do instead is I'm going to actually call this. Let's see the way I'm going to do it. I'm going to do IXX X, let's see, I'm looking at the way I did it before. IXX. I'm going to call, this is an X. I'm going to call this the vector IX. So they'll have components IXX, IXY, IXZ. And then this I'll call the vector IY, and this I'll call the vector IZ. And then my I will just be a list of IX, IY, IZ. So then I can have a list of vectors, and that is the same as this. Does that make sense? Okay, so it's a workaround. It's a workaround. So going back to the computer. So let's define our moment of inertia tensor. I want more space. I like that better. Okay, so I'm going to say def I, and I want to pass it two things. I want to pass it my center of mass, my point about which I'm going to calculate. I'm going to call that RO, and then my mass is ms. And we're using the same thing from before because no one can stop me, even if it's a bad idea. I'm unstoppable. Okay, so let's put in here RO is the point about which I is calculated. I is calc. And then ms is list of masses. And they're objects. Okay. So the first thing I want to do is to start off with, again, I'm going to calculate a lot like I did the center mass. I'm going to say IXX equals 0, IXY equals 0, IXZ equals 0, 0, 0. And then I'm going to do IYZ equals 0. I don't need to do IYX because that's the same as IXY, right? They're the same. And then I need to do YZ equals 0. Let's see, IYY equals 0. I need to do IYZ equals 0. And finally, IZZ equals 0. So then when I add all these things together, I have something to add them to. Okay, so now let's go and say, do another loop through all the masses. Let's call them, what did I call them before? For MM. Let's do that again. For MM in MS. So MM is my mass. So I want to calculate IXX. So IXX is going to be the old IXX plus the mass MM.M times its y value squared plus its x value squared. So it's going to be mm.pos.y squared plus mm.pos.z squared. So remember, POS is my position. Oh, but I made a mistake. That is with respect to the origin. In fact, what I want to do is this. Minus ro.pos.y. Right? So I want to get its position with respect to the point that I want to calculate. And the same thing over here too. So minus ro.z. Actually, this is just .z. It's not an actual point. It's just a vector. So it's just going to be like that. Okay. So now I need to do the same thing. Let's do IXY. That's going to be IXY plus minus, right? Because it has a minus. Minus mm.m times mm.pos, parentheses, double parentheses, mm.pos.x minus ro.x times mm.pos.y minus ro.y. That's it. Okay, now we're going right along. Let's get all these other ones in here. I'm going to copy that. And let's do let's see, I did XY. I'm looking at this with list XZ. So I'm just going to change this to Z, Z, that's that, and this is going to be Z. Okay, now I need to do, I'm looking at my list right here. I did that one. Let's do YZ. So let's paste that again. So it's going to be YZ, YZ, and it's going to be Y. It doesn't matter which one it is. Y. Oh, I didn't need to change that. That's fine. You make mistakes, it's cool. Okay, so now I need to do y, so I'm going to copy this. Let's do these other ones first. So I did y, I need to do yz. I did that one. Did I get them all? See, so I should have ixy, got that, ixz, iyz. I got iyz in there twice. So I don't need that. Let's see. 1, 2, 3, 4, 5, 6. Well, I should have 6. 1, 2. That's right. Okay. So now I can do iyy. So I'm going to copy this. And then change these to z. Let's see. Yy is xz. And then call this yy. And then let's do it again for z. And this is going to be, let's just change that to x, zz, zz. Okay, so now I need to, 1, 2, 3, 4, 5, 6, that's it. Now I'm going to return, I'm going to build my, no, I'm just going to return it. No, I am going to do this. Let's call ix as the vector, let's see, it's ix is the vector ixx, ixy, ixz, just like we have in the thing. Iy is the vector yx, which I don't have, right? I don't have yx, so I'm going to put xy, iyy, iyz. Did I calculate yz? Yeah, I did. And then finally, iz is the vector ixz, same as before, iyz, izz. Oh, there's a lot of stuff here. I get it. Okay. Now I'm going to return the list ix, iy, iz. Whew. Okay, let's see if this thing works. Oops, this should be dedented because it's outside that list. This should be dedented. Right, I only need to calculate those once. Okay, so let's try and see if this works. So the first thing I'm going to do is get my center of mass. I'm going to call it RC is RCOM masses. That's what I call my things, right? Masses, right? And then I'm going to say IT for temp. I can't call it I. That's my other function. So it's going to be I. I'm going to pass to it RC and masses. And let's print those. Let's just print IT. I equals IT. And I'm not going to put the units. I'm not even sure this is going to work, but I should save it. Don't you think I should save it? Run. Okay. So, I mean, I don't know for sure that's right, but it looks right. Notice I have a vector. So I have a list of vectors, and that's like my inertia tensor. Does that make sense? Whew. Okay. So now what we want to do is to, I want to take an angular velocity vector and operate it on that inertia tensor. Let's go back to the paper and think about how we're going to do this. So going to paper. So let's take what we want to do. So here's I want to do this operation. So let's say omega is the, is the vector omega x, omega y, omega z. It's got 3 components. And I want to operate that on I. So here's my I omega. It's going to be, let's call this, I guess I should write it out, IXX, IXY, IXZ, IYX. I had a little mental breakdown there. IYZ, IZX, I, Z, Y, I, Z, Z. And I'm going to operate on this vector omega x, omega y, omega z. And how do I do that? Well, I'm going to take this and basically take the dot product of that. But this is already a vector, right? So I can actually write this as ix vector, iy vector, that's a y, iz vector, omega x, omega y, omega z will give me, this is a vector. So this is going to give me the vector, I can write it as a vertical vector, omega dot ix. That's what's going to go right here. It's going to be this and that. Omega dot iy, omega dot iz. And so the dot product is built into Python, so that's pretty cool. Let's just go ahead and make this also as a function. I know, there's a lot of stuff going on here. But we're going to make it work. Once we make it work, we can make it work for other things, and that's important. So let's define one more function, def. I'm going to call it m dot. And it's going to be the matrix multiplication, that's what the m's for, between A and B. So A is a matrix, not really, and B is a vector. So I have to pass it a list of vectors for A. If I don't, it's not going to work. So what I'm going to do is to say Cx, the x component of the resultant, is going to be equal to, my resultant is C. It's going to be the dot product of A0, the first element in there, and B. So that's going to give one single value. Cy is going to be the dot product of A1, which is the Iy, and B. And then finally, Cz is going to be the dot product of A2 and B. And then I'm going to return the vector Cx, Cy, Cz. So now I can take dot products. So let's just go ahead and do this. I already have I already have the center mass, all that stuff. Let's say omega is the vector 1, 0, 0. It's just in the x direction. I don't really care. I want to calculate L. So let's say L is going to be m dot I t, I call it it, and omega. And let's print that. So let's print omega. And you can do this manually to make sure it's working, but I'm pretty sure it is working, so I don't really care. Omega. I'm not going to leave the. I'm not going to put the units there. And then print L equals L. And let's see if it works. I don't know that it's going to work. You never know if these things are going to work. You got to try it. Okay, it looks like it works. So I have an angular velocity in the x direction. My angular momentum is in a different direction. Notice that different direction. That's kind of cool. Let's do this because it will be fun. I want to make a vector I want to draw a vector for both omega and L. So let's go back up here. I'm going to say scale equals 0.5. So because I want to draw a vector. The length of the vector is in meters, technically, because I'm drawing it, but the angular momentum and the angular velocity might be too big. So I need to scale, and I'm just going to pick a value and then adjust it. So I will call W arrow my angular velocity vector, and it's going to be an arrow. Its position is going to be the center mass, which is RC. Its axis is going to be equal to scale times omega. That's the direction. And let's make this color equals color dot purple. I don't know why I just picked purple, but purple as it is. And let's do L arrow is an arrow, position equals RC, axis equals scale times L, and color equals color dot yellow. Let's run it. Okay, so there is way too big. So let's do this. Actually, also my values can be different. Let's do I don't really care about the magnitudes. I just care about the direction. So let's call this norm omega. and let's call this norm L. Right, that will return the unit vector in that direction, because I don't really care about the length. I just want to know the directions. Okay, so there's my 2 vectors. That purple is not working for me. I'm going to change this to red. Let's do cyan. And the scale's too big. Let's try 0.1. Okay, I'm pretty happy. So there's my angular velocity vector. There's my angular momentum vector. Let's change the angular velocity vector. Let's try an angular velocity in the z direction. So 0, 0, 1. And now let's run it. So here you can see that I only see the angular momentum vector because they're the same. So if I rotate this in the z direction, angular velocity and angular momentum are in the same direction, and that's kind of cool. Now, let's pick another direction. Let's do the y direction. 1, 0, 0. Let's run that. Now, they're not in the same direction again. Okay, so this is really the next thing that we're going to do. I'm not going to do this in this video, but it's how do we find the directions of the angular velocity so that they're in the same direction as the angular momentum. And there's the right way to do it, and then there's the my way to do it. And I'm going to do it my way because I think it's more fun. And so basically, spoiler alert, here's what I'm going to do. I'm going to rotate that angular velocity vector until it's in the same direction as the angular momentum, and that's how I'm going to find that. There is another way to do it, but I like this way better. So, okay. I'm going to give you the link to this code. Hopefully you learned something about lists and matrix operations and functions, but maybe you just saw some cool pictures of arrows and dots too, so that's cool too. That's it.